pretty good, so I'm pretty happy with your homework submissions. And again, if you haven't been submitting the homework, I highly encourage you to do it. And I will leave comments on your homework to help you in the problem areas. So yeah, today's the homework from the previous lesson looked pretty good. There were a few common mistakes. So here there are 2 points I want to clarify. So the first thing I want to point out is that for the compounds that we're looking at, the charges are already all indicated. We already know the charges of all ions, and from the charges we can come up with the chemical formula. Because of that, we don't need to put prefixes in front of the cation and anion name. For example, let's look at the barium chloride, right? So we know that the barium is +2, and we know that the chlorine is -1. So if you were to write barium dichloride, this di isn't necessary. So we don't need to write the di prefix for or tri or mono, etc. We don't need to write those prefixes for these kinds of compounds. But some of the compounds that we'll look at today, they do require prefixes. So we'll talk about that later. And one final point I want to clarify, I don't think I made this very clear. So how do we remove electrons to fill ions? So let's look at PB. So PB should be Xe6s2 5d 4 F14 5d10 and 6p2, right? Does everyone agree with that for lead? Oh, so does everyone have a periodic table with them? Because I don't have mine, so I'm trying to do this from memory. Okay, so so lead forms two charges, so we can have Pb 2+ and Pb 4+. So to form the 2+ ion, we remove the p electrons first, and to remove the to create the 4+ ion, then we remove the s electrons. So we remove p, then s, then d, then f, right? So s, okay. Oh, so p before s, before d, before f. But usually you won't have to worry about those two. Does that make sense? Great. Yeah, I wouldn't worry too much about the f electrons for now. Just ignore them since a lot of their so the f block is the lanthanides and the actinides, and both of them are incredibly boring. So you don't need to worry too much about that. The one thing I would know is that most of the lanthanides, so the elements starting from lanthanum to lutetium, I think. So if that's right, so La to Lu, most of them will be 3+. And then actinide chemistry, so the stuff, so the row from actinium to something I can't remember, like fermium or something like that. So the bottom row of the F block is very complicated, so you don't need to know about that. Okay, so with that out of the way, so I think you guys did well on the homework, so that's good. Did everyone have a chance to look at the handout I posted on acids? Right. So do we have any questions about that? Nope. Okay. So I guess we can start lesson 3 now. So today we're going to be talking about Lewis structures, and if we have time, we might cover some molecular geometry. And if not, I've made a handout for that. Okay. So first I want to cover why is this stuff important? Okay. So most of the compounds that exist out there, so basically all of organic chemistry, involve like the kind of bonding that we're going to talk about, and especially in organic chemistry, the idea of structures and shapes are really important. Like with our ionic compounds we talked about in lecture 2, there's not really much to talk about shapes or structures and anything, and their greater crystal structure is something we'll talk about later, but they don't really involve like geometric shapes, but this becomes important here. Also, additionally, these properties that we're going to talk about at the atomic level determine some macroscopic observations. So, for example, the high boiling point of water can be partially explained by the shape of the water molecule. Yeah. And this stuff is incredibly crucial for more advanced topics in chemistry. So, like what I mentioned, organic chemistry, and it is part of the AP and SAT curriculum. So first, I want to review ions real quick. So a metal plus a non-metal gives an ionic compound. So these are the simple ionic compounds, not with our polyatomic ions. So the metal sodium plus a non-metal chlorine goes to this ionic compound. So table salt. So the cation will lose an electron and the anion will gain the electron. And both the cation and the anion have a noble gas configuration, okay? So why does this work? So the metals are willing to give up their outer electrons, and the nonmetals are willing to accept them, okay? So you might say that the nonmetals have a greater attraction for electron, and this idea can be summed up with electronegativity. So the idea of electronegativity was first formulated by Linus Pauling, so the guy whose picture I have here, and he's considered by some to be like the greatest American chemist, so Nobel Prize winner. And he actually became somewhat of a celebrity in the 50s and 60s because he advocated for eating lots of vitamin C to cure disease. So he believed that if you took a ton of vitamins, way more than you need, your diseases will go away. And all of this was proven false. Like this is pseudoscience and alternative medicine. But so that's how he got, so he became somewhat of a celebrity back then. Okay, so the electronegativity, you can think of it as a measure of how much an atom wants electrons. So more electronegative elements are close to the upper right, and what are called the electropositive elements are closer to this area of the periodic table. So you can see these ones have greater values of electronegativity, and these ones have low values of electronegativity. And ionic compounds form with compounds when you have the two elements have a very large electronegativity difference. So this means, for example, sodium chloride. So sodium is about 1 and chlorine is about 3. So the difference is 2, which is greater than 1.7. So this would be considered an ionic compound. Yeah, don't worry about the 1.7 rule too much. This stuff is obviously like very flexible. So basically, the chlorine is very electronegative, it's very willing to accept those electrons, and the sodium is not too attracted to the electrons, so it's willing to give them up. So as another example, calcium and bromine. So that's another big difference. So we have calcium bromide, and the biggest difference is cesium and fluorine. So fluorine is the most electronegative element. Okay. So do you have any questions on electronegativity? Great. So now we can talk about covalent bonding. So this is the meat and potatoes of this lecture. So we already know what happens when we have a large electronegativity difference. But what happens when we have similar electronegativities? So this means that neither atom really wants to give up its electrons and neither atom wants to really accept electrons. So for example, a nonmetal plus a nonmetal. So this is where we typically find this stuff. So basically, The atoms will share their electrons so that each atom has 8 what are called valence electrons. So the valence electrons are the outermost shell. So, and what I mean by outermost shell is what I mean by the value of n. So let me just give you an example. For example, oxygen. So 1s2, 2s2, and 2p4, right? I think that's right. So the largest value of n, and the largest value is 2, so then we sum these numbers together. So this tells us we have 6 valence electrons. So I guess that's the easiest way of thinking about it. And at least for covalent bonding, it's easier to ignore the d electrons for now. And if you want to learn more about how the d electrons participate in bonding, you can go read a book about inorganic chemistry. So it's very interesting stuff, but yeah, we don't need to talk about it right now. Okay, so why 8 valence electrons? Because you want to fill the s electrons and the p electron, the s orbitals and the p orbitals. So remember that an s orbital can fit 2 electrons, and the p orbit and the three different p orbitals each hold 2 electrons. So in total we get 6 electrons. So this gives us a grand total of 8 valence electrons. So this is known as what's called the octet rule. And there are 1 million exceptions to the octet rule, which we might talk about later. So, but the 2 big ones for now are hydrogen and boron. So basically, hydrogen only really needs 2 electrons, right? Because the p orbitals are very high in energy for the hydrogen atom, so we can ignore those. So all we need to consider is the 1s orbitals, so 2 electrons. And boron often has an incomplete octet, so oftentimes we'll have less than the required 8 electrons. So but we'll talk about that when we come to that. So let's look at example 1. So dichlorine, so chlorine gas. So here's the electron configuration of chlorine. Right? You all agree? Okay. So as you can see, we have 7 valence electrons. 2 plus 5 is 7. So we need 1 more to fill the octet rule. And so to get this 1 electron, we need to form 1 bond to get that electron. So this means that dichlorine has what we would call a single bond. So each atom will share 1 electron. And this means that the chemical bond involves 2 electrons. So we could call this a bonding pair. So I guess I can show you a better illustration of this. So Cl, so our 7 valence electrons, right? And then I will draw a little circle. So this electron gets shared with this chlorine. The electron from the other chlorine atom gets shared, and then the same thing happens here. So then these 2 electrons form the bonding pair. Do we have any questions about that? So I'll give you a second to draw this on your notebooks or whatever. Okay. Let's look at slightly more complicated example. So dioxygen, so this is the stuff we breathe. So here's the electron configuration of oxygen. So as you can see, we have 6 valence electrons. So we need 2 more electrons. So oxygen can form 2 bonds. So this means it will either form 2 single bonds or 1 double bond, usually. So oxygen will have a double bond. So I can draw that for you. So our 6 valence electrons, and then they get shared like that. So here we have a double bond. So the double bond involves 4 electrons. So 1, 2, 3, 4. Any questions? No? Okay. So, okay. So remember that hydrogen is an exception to the octet rule, and we only need 2 electrons. So try to draw a hydrogen molecule yourself. So I'll give you a minute to do that. So draw the hydrogen atoms and the electrons. And by the way, you might have heard of dot and cross diagrams. I don't use them, but it might be helpful for you. So to use a dot and cross diagram, you represent the electrons coming from one atom as a dot, and from the other atom, you use a cross. So I'll pull this up, so if you need help, you can look at this diagram. Okay. So let's just go over this example. So what you should have drawn is, okay, so I'll use the dot and cross diagram, so it might be helpful. So we have an H, and then we use a dot, and then an H and a cross. And then each one of these hydrogens wants 2 electrons. So they share it like this. So we should have an H each single bond. Let's do a slightly harder example. So let's do nitrogen. Right. So nitrogen is He2S2, 2P3. So try to draw a nitrogen molecule and tell me what kind of bond does it have. Does it have a single bond, double bond, triple bond, quadruple bond? So. And I'll give you guys a minute to do this too. So tell me when in the chat if you're done drawing your picture, and tell me what kind of bond it has. Does everyone agree with Andrew's answer? Yeah. Great. So Andrew's right, and N2 does have a triple bond. So how do I go? That's right. So each nitrogen comes with 5 electrons, and it needs 3 more. So it shares with 3 electrons from another nitrogen atom. Okay, and I think we should do a somewhat more complicated example. So let's do 2 more examples. So far we've been sticking with homonuclear diatomics. So let's do one more. This one's a bit tricky. So carbon monoxide. And let's do CO2. So try to draw both of these. Carbon monoxide is a little tricky. So yeah. So if you can't get it, just move on to CO2. So does anyone know what type of bond is in carbon monoxide? Oh, by the way, so the connectivity in CO2 is like this. So we have a central carbon atom and then 2 oxygen atoms on the side. So that might help. Okay. Do you guys want to keep working, or do you want me to give you do you want me to go over the answer? Okay, so let's look at the answer for these. So carbon monoxide, let's do carbon dioxide first. So can someone tell me how many, yes, it is a triple bond, but, and we'll get to that in a second. So can someone tell me how many valence electrons carbon has? Right, here's the electron configuration, 4, great. So it has 4 valence electrons. And then how many does oxygen have? Great, 6. So I'll draw those. Okay. So now the carbon atom needs 4 more electrons. So it will share some electrons with oxygen. So it will share these 2 with oxygen. And then, oh, I did not draw this well. And then these 2 with oxygen. So now you can see in total, carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And we've fulfilled the octet rule. So, and then you can see oxygen also has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And 1, 2, 3, 4, 5, 6, 7, 8 electrons. So everything's good. And then you can draw this as this. So one thing I want you to notice from the previous exercises is that carbon tends to form 4 bonds. So carbon. Nitrogen usually likes to form 3 bonds. And then oxygen usually forms 2 bonds. There are, of course, exceptions to this, however. So, and carbon monoxide is one of those exceptions. So your first instinct might be to draw a double bond between carbon and oxygen. So it would look like this, right? And I'll draw the full picture out for your convenience. Does that make sense? Okay. So this is almost right. Maybe 50% right. And then, but you might notice is that the oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons, right? Because the double bond is 4 electrons. However, the carbon atom has 1, 2, 3, 4, 5, 6 electrons. So this carbon atom is not following the octet rule. So how do we solve this? We take the 2 electrons on the oxygen, and then we move them to form a bond. So usually when we draw the movement of electrons, we draw an arrow. And then the end result is this. And then, and I want you to confirm by yourselves that this follows the octet rule. Okay? And remember, and the strange thing about this is that both of the electrons from the bond come from oxygen. So it's almost like the oxygen is giving electrons to carbon in a way. So because of this, we call this a dative bond. Right? Does that make sense? Do you have any questions about carbon monoxide? Okay. And because these concepts are so important to get, how about we do one more example? So, N, let's do N2H4. So the shape is like this. And H2O2. So like this. Okay, so can we do those 2 examples? And let me look something up real quick. Can't remember what the name is. Oh, diacene? Okay. And I'll write the names of these compounds, by the way. Okay. So I'll give you guys 5 minutes to draw the bonds in these compounds. I'll do one more. Okay. So do you guys want to keep working? I don't know how foreign this stuff is. Like, I don't really have a sense of how well you understand the material here. So I want to make sure that there's not some crucial information here I forgot to say. So, so does anyone have any answers right now? Okay, great. So how about this? Let's do this. So on a scale from 1 to 10, how well do you understand this stuff? So okay, that's good. Okay. So how about let's just do this process really step by step. So, okay. So each dot represents an electron. So let's put in our electrons first. So each hydrogen has one valence electron, which we will represent as a single dot. Okay. And now let's do this in a different color. So can someone tell me how many valence electrons nitrogen has? Okay, great. So 5 valence electrons. So I'll fill those in. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Okay. Ignore this little speck there. Okay. So can someone tell me how many valence electrons oxygen has? Great. So 6. So let's fill those in. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. And what about carbon? 4? Okay, great. So 4. So I'll put that in. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so now we can start to draw our bonds. By the way, do you guys want me to draw the little circles, or is it okay if I just draw a line to represent a bond? Right. So let me use a different color. So here is a slightly darker shade of blue. Great. So this hydrogen wants another electron, so we'll give it its electron. So does this hydrogen, and these hydrogens also want their electrons. Okay. So does anyone have any questions about what I just did? Okay. Good. So now, so the hydrogens have satisfied the octet, the rules. So they each have 2 electrons, so that's good. However, the nitrogens, as you can see, only have 1, 2, 3, 4, 5, 6, 7. So they will also form a bond. So see, we get a bond formation here. So now let's draw this in a more concise form. Great. Okay. So as so I want you to, so can you see that? So each bond contains 2 electrons. So 2, 4, 6, and then 7, 8. So we've fulfilled the octet rule here. And as you notice, this one also follows the rules, since each nitrogen forms 1, 2, 3 bonds. Okay. So by the way, so hydrazine is a very toxic liquid, and it's used as a rocket fuel. So that's why if you ever see like this pictures of like the space shuttle landing, right? Everyone is like wearing these hazmat suits because the space shuttle uses hydrazine to control its orientation. So very toxic. So let's look at our next molecule. So again, we can form the bonds between the hydrogens and the oxygens. And as you can see, we have 1, 2, 3, 4, 5, 6, 7 electrons. So we're missing 1. So we'll form a single bond here. So now each oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So we'll draw this like this. Okay. So I think, so you all have probably seen hydrogen peroxide, right? So hydrogen peroxide can be used as a disinfectant, but at high concentrations, it's also a rocket fuel. So all of these things are rocket fuels, great. Okay, so let's do acetylene. This one's a little trickier. So again, we'll form our bond, our carbon-hydrogen bond. So now, can someone tell me how many electrons each carbon atom has right now? So does everyone agree with Brian and Kathy? Well, okay. So everyone agrees with you, that's good. So yeah, they're right. So right now we have 5 electrons, so we need 3 more. So how do we get these 3 electrons? We need to form a triple bond between the carbons. So this, our ending picture should look like this. Okay, so what is acetylene used for? So back when, back before electric lighting, so for car headlamps, they would use acetylene to power their headlamps. And acetylene is kind of interesting from a chemistry standpoint because of how it's made. So you react calcium and carbon to form calcium carbide. I think that's right, right? And then this reacts with water to form acetylene and calcium hydroxide. So basically, this is how those car headlamps would work. So you would take the sample of calcium carbide and you would drip water onto it. So this would slowly release acetylene gas, which could then be used by your car light. Also, this is a great way to make a simple organic molecule. So it has carbon and hydrogen. Like organic compound from very simple starting materials. So, yeah. And acetylene can be used for many has many uses in organic chemistry. Okay. So I think we can move on to our next topic now. So Lewis structures. So I already gave you a taste of Lewis structures, but so basically, instead of drawing these very clunky diagrams, we represent the shared electrons with a line. So this represents a bond. So each line represents 2 electrons. So can someone tell me how many electrons are in this bond? This oxygen-oxygen double bond? 4, great. So yeah, this represents 4 electrons. So one important thing I want to note is that the total number of valence electrons that you've drawn should be the same as what you started with. And then you might add 1 or 2 or subtract some depending on the charge. Okay? So for example, so oxygen, has 6 valence electrons. And since we have 2 oxygen atoms here, we should have 12 total electrons to work with. So now if we count up the electrons here, we have 1, 2, 3, 4, 5, 6, 7, 8, plus 4, so we have 12. So it's the same as what we started with. So, okay. Now let's do some problems. So draw the Lewis structures for H2O and CO2, and you can ignore the last one since we just did that. Have you all drawn, so how are we doing? How's the progress? Scale from 1 to 10. Done, so that's good. Okay. Oh, so this is perfect. So it seems like a lot of you are getting this material. So hopefully we can breeze through it and we can talk about some more interesting stuff. So, okay. So just to confirm the answers. So let's do this. So the oxygen, and then we have an H and an H. So each hydrogen wants 2 electrons, so it forms a single bond. And now this oxygen needs, so it has 1, 2, 3, 4, 1, 2, 3, 4 electrons, so we need 4 more. So just put it here. And now, okay, and that's it. And then for CO2, each carbon wants 4 bonds, so, and then each oxygen wants 2. And then we just fill in the lone pairs. Okay. Great. So now let's talk about formal charge. Oops. Okay. So the idea behind formal, so here's the procedure for generating your formal charges. You take these bonds and you split them evenly between the atoms that form the bond. Then you count up the total number of electrons that that each atom has. And then you compare this to the number of valence electrons in the neutral atom. So if it has more electrons, it has a minus charge. If it has less electrons, you get a plus charge. And one important thing to note is that the sum of the formal charges should equal the charge on the overall molecule. Okay? So I'll illustrate this with a few examples. So by the way, let's talk about formaldehyde, so CH2, CH2O, so kind of an interesting compound. It's very reactive. This carbon atom is very reactive, and it's used to preserve biological samples, so like cadavers, for example. So it's used in the embalming industry. Okay, so let's do the hydrogen atom first. So how many, can someone tell me how many electrons are in this bond? Great, 2. So you have 2 bonds, 2 electrons. So we split those 2 electrons between the carbon and the hydrogen. So we give 1 electron to carbon, 1 electron to hydrogen. So now our hydrogen has 1 electron, and a neutral hydrogen atom also has 1 valence electron. So the difference is 0. So that's the formal charge. And okay, so now this carbon atom, it gets 1 electron from this bond, 1 electron from this bond, and then can someone tell me how many electrons it will get from this bond, this double bond? Okay, so so the double bond contains 4 electrons, and we give half of them to carbon. So we give half of those electrons to carbon. So we have 1, 2, and then 3, 4. So 4 minus 4 is 0. Okay. So now for oxygen, we get 2 electrons from the double bond. So 2 electrons from the double bond, plus 4 electrons from our lone pairs. So these dots are called lone pairs. So this gives us a total of 1, 2, 3, 4, 5, 6 electrons. And the neutral oxygen atom also has 6 valence electrons. So it's another 0 formal charge. So let's do another example. So carbon monoxide. So does anyone know why carbon monoxide is toxic? Just out of curiosity. And you learned this in biology class? Okay. So basically, does anyone know the name of the protein that carries oxygen in our blood? So the protein that carries oxygen in our blood is called hemoglobin. So hemoglobin basically looks a little like this. So we have this huge protein off to the side, which we don't draw because it would be too big. And then the important part of the protein is this ring surrounding the iron. So that ring is called a porphyrin ring. I don't know how to spell that, by the way. So then we have this portion of the molecule. So this comes from the amino acid histidine. So histidine for those who are wondering. So if you're wondering. So histidine. So the 4 nitrogens on the porphyrin bond with this iron. And then we have another nitrogen bonding to the iron. But the iron likes to have 6 bonds. So for reasons you don't even need to worry about. So it has one empty space. It has one empty space that an oxygen molecule can bind to. So this is how this molecule, this hemoglobin, transports oxygen. And this bond is is relatively weak. So the binding of oxygen is reversible. So this means, okay, so in your lungs, it will bind to oxygen, then the hemoglobin will travel through your body, and then the oxygen can come off, and then your cell uses the oxygen. So everything's great, right? Okay, so what happens when you breathe in some carbon monoxide? So for reasons that we don't need to go into, but actually we might if we have enough time at the end of the lecture. So the carbon monoxide has a very strong bond with the iron. So that means it blocks this site on the iron, and now there's no space for the oxygen to bind to. So that means that your hemoglobin molecules in your body can't transport oxygen throughout the body anymore. So, and then you die because you don't have any oxygen. So that's why carbon monoxide is toxic. Okay, so let's do the formal charges on carbon monoxide. Oh, how do I move the camera? Okay. Like this, right? So first, just to make things easier, we can draw it like this. Oh, that should be okay. So we have the triple bond here. So now we split these electrons evenly. So now we're left with this. Okay, so now we have this. Can someone tell me what the formal charges are now? So what's the formal charge on carbon and oxygen? So remember that a neutral carbon atom has 4 valence electrons. So here our carbon atom has 1, 2, 3, 4, 5 electrons. So so that means it has 1 extra electron, which gives it a 1 minus charge because electrons are negative, right? So we can write a -1 here. What about this oxygen atom? How many electrons does a neutral oxygen atom have? Valence electrons. Right, 6. So we have only 5 electrons here. So that, because we have 1 less electron, that means we have a +1 charge, because removing electrons gives stuff positive charge, right? So these are the formal charges of carbon monoxide. How about let's do one more example and then a 10-minute break. Yeah, so let me think. Let's do one more example and then a 10-minute break. So let's do so the ammonium ion. So I'll give you guys a minute to determine the formal charges here. Just tell me what the formal charge on nitrogen is when you're done. I think, Andro, your mistake was that you considered all of the electrons in nitrogen. You don't need to consider the 1s electrons because because we don't need to worry about those right now. We only need to consider the valence electrons, so the electrons in the outermost orbitals, so the 2s and the 2p orbitals. So there we have 5 electrons, right? So yeah, +1 is right. So we give 1 electron to nitrogen. So then our nitrogen has 4 electrons, so it gives it a +1. And you'll notice that this formal charge is the same as the total ion. So we've got it right. Great. So let's take a 10-minute break right now.